When people say Linux feels faster, they're often not talking about raw benchmark numbers. They're describing something more subtle and more human. The way the desktop responds, the way windows appear instantly, the way the system seems to stay out of your way. You click, and something happens. You drag a window, and it moves without hesitation. You open a file manager, and it appears as if it was already waiting for you. On the exact same hardware where another operating system might feel slightly heavy, slightly delayed, slightly preoccupied with itself, Linux can feel light, direct, and eager. That feeling starts long before you even reach the desktop. The boot process on many Linux systems is lean and intentional. There are fewer background services starting without your knowledge, fewer bundled components assuming they must exist. Most Linux distributions are built around the philosophy that the system should do exactly what is required and nothing more. That minimalism affects everything. The kernel initializes hardware, loads only necessary drivers, and hands off control to user space with a level of efficiency that has been refined for decades. It's not flashy. It's focused. One of the biggest reasons Linux desktops feel faster is simply the number of background processes running at idle. On a typical Linux install, especially with distributions that prioritize efficiency, the idle memory footprint is dramatically lower than many mainstream operating systems. Instead of consuming gigabytes of RAM before you even open a browser, Linux might sit comfortably using a fraction of that. Memory that isn't being used by the system is available for your applications. That changes responsiveness in subtle but important ways. Applications launch faster because the system doesn't need to aggressively swap or reclaim memory. File caching becomes more effective. Disk reads are reduced. Everything feels smoother because the system isn't fighting itself for resources. Then there's the absence of constant background indexing, telemetry collection, advertising frameworks, and layered compatibility services. Linux doesn't ship with embedded ad services. It doesn't continuously synchronize system-level cloud features unless you configure it to do so. It doesn't reserve system cycles for background ecosystem integration that you may not even use. The CPU scheduler can prioritize what you're actually doing rather than what the operating system assumes might be important. The Linux kernel scheduler is another major piece of the puzzle. Designed for scalability, from embedded devices to supercomputers, it handles process prioritization with impressive efficiency. Interactive tasks are treated differently from background tasks. When you move your mouse or type on the keyboard, the scheduler prioritizes responsiveness. That's why even under load, a Linux system often remains usable. You can compile code in the background, run virtual machines, and still experience fluid desktop interaction. The system doesn't lock up or stutter as easily because the scheduler is optimized to keep the user interface responsive. Desktop environments also play a role. On Linux, you aren't locked into a single graphical shell. You can choose between lightweight environments like XFCE or LXQT, balanced options like Cinnamon or Mate, or more modern and visually polished environments like GNOME and KDE Plasma. That choice matters. If you're on older hardware, you can select an environment that consumes minimal system resources. Even on powerful machines, the flexibility allows you to tailor the experience. The operating system adapts to you rather than the other way around. Even the way Linux handles window compositing can feel more efficient. Many Linux desktops use compositors that are either integrated efficiently into the window manager or can be configured precisely. Wayland, the newer display protocol, reduces layers of abstraction that previously existed under X11. With fewer translation layers between application and display server, rendering can be more direct. The result is smoother animations and lower latency, especially on modern hardware. Windows appear instantly, not because they're magically faster, but because the graphics stack is streamlined. File systems are another underappreciated factor. Linux file systems like X4, BTRFs, and XFS are mature, efficient, and designed with performance in mind. Metadata operations, which affect how quickly files and directories open, are often extremely fast. Opening a folder with thousands of files doesn't necessarily cause the same pause you might expect elsewhere. Copy operations, especially within the same partition, can feel instantaneous due to copy-on-write optimizations in certain file systems. That perceived speed reinforces the sense that the desktop is agile. Package management also contributes to the feeling of efficiency. Instead of running multiple hidden installers, update services, and background updaters from different vendors, Linux typically centralizes software management. A single package manager handles installation, updates, and removal. That reduces duplication. It reduces background activity. It reduces fragmentation. When updates occur, they're often cohesive and controlled. You're less likely to experience sudden system slowdowns because a background updater decided to monopolize disk I/O. Another reason Linux feels faster is psychological, but rooted in design philosophy. Linux systems tend to avoid unnecessary visual noise. There are fewer pop-ups, fewer unsolicited notifications, fewer suggested features. The desktop isn't trying to guide you toward a subscription or upsell. It's trying to function. Clarity reduces cognitive load. When your system behaves predictably, it feels faster. Responsiveness is not just about milliseconds, it's about friction. Driver models also matter. The Linux kernel includes a vast number of drivers built directly into it. This unified driver architecture means there's less overhead from separate driver frameworks running independently. For many devices, especially older hardware, Linux drivers are lean and stable. They don't include large companion suites consuming background resources. Your network driver doesn't come with a branded control center running in the system tray. Your GPU driver, depending on the vendor, might integrate cleanly without layered telemetry or service daemons. Security architecture contributes indirectly to performance. Linux permission models are straightforward. There's less reliance on constantly running security agents that scan every file access in real time. While security tools exist and can be installed, they aren't always mandatory or intrusive. This reduces disk scanning overhead and CPU usage in day-to-day operations. Then there's the modular nature of Linux. Components are separate and replaceable. If a service isn't needed, it can be disabled. If a feature isn't useful, it can be removed. This modularity means your system can be trimmed down to exactly what you require. Contrast that with monolithic systems where certain components are permanently integrated and cannot be removed without destabilizing the OS. When you remove excess weight, performance improves. The way Linux handles memory caching also influences responsiveness. Linux aggressively uses free memory for disk caching. That means frequently accessed files remain in RAM. Applications you open often will launch almost instantly after the first run. Instead of keeping RAM artificially free for cosmetic reasons, Linux treats unused memory as wasted potential. The result is a system that feels increasingly responsive the longer it runs. Swap behavior is another subtle factor. Linux allows granular control over swappiness, how aggressively the system moves memory pages to disk. By tuning this parameter, users can optimize responsiveness. Even without manual tuning, many distributions choose conservative defaults that prioritize interactive performance. When RAM pressure increases, the system doesn't immediately degrade into heavy disk thrashing. Transparency also plays a role. On Linux, you can see exactly what's running. Tools like top, atop, and system monitors show real-time resource usage. If something is consuming CPU cycles, you can identify and stop it. There are no mysterious processes with obscure names that resist termination. That sense of control reinforces the feeling of efficiency because inefficiency can be addressed directly. Even the culture around Linux development impacts performance. Open-source communities often prioritize code review and optimization. Bloat is criticized. Redundancy is questioned. If a desktop environment becomes heavy, forks and alternatives emerge. Competition within the ecosystem drives efficiency. Developers are not bound by corporate mandates to integrate revenue-generating services. They focus on functionality and user experience. Compilation models can also matter. Many Linux distributions compile software optimized for general hardware targets, but some allow users to build from source with architecture-specific optimizations. This can squeeze additional performance out of the same machine. While not everyone does this, the possibility reflects the system's flexibility. Network performance often feels snappier as well. The Linux networking stack is renowned for stability and efficiency. Many servers on the internet run Linux for this reason. On the desktop, that same stack handles everyday browsing and downloads. Latency feels low. Throughput remains stable. There's little interference from background bandwidth consumption unless explicitly configured. Power management is another dimension. Linux can be extremely efficient at managing CPU frequency scaling. It can ramp up performance instantly when needed and scale down to conserve energy when idle. That dynamic adjustment keeps the system feeling responsive without running at maximum power constantly. The CPU isn't throttled unnecessarily, nor is it locked into high usage when idle. When comparing two operating systems on identical hardware, small differences accumulate. 10% less memory usage, fewer background disk writes, slightly lower input latency, reduced animation overhead. Individually, these differences might be subtle. Together, they transform the experience. The desktop feels alive rather than burdened. The lack of forced restarts also affects perception. Linux updates rarely require full system reboots. You can update most applications and even many system components without restarting. That continuity means the system feels stable and persistent. It doesn't interrupt your workflow with mandatory downtime. Even window management design choices contribute. Linux window managers are often keyboard-friendly and efficient. Tiling window managers, in particular, eliminate animation overhead entirely. Windows snap instantly into place. There's no dragging or resizing delay. For users who adopt these environments, productivity and perceived speed increase dramatically. It's also worth noting that Linux tends to age gracefully on hardware. Systems that feel slow under other operating systems often regain usability under Linux. That's because Linux distributions can be chosen to match hardware capability precisely. Instead of forcing modern visual effects onto aging GPUs, you can select a lightweight stack that respects hardware limitations. Finally, there's an intangible element: intentionality. Linux systems are often installed by choice, configured deliberately, and maintained with awareness. Users disable what they don't need. They choose environments that fit their workflow. That intentional configuration reduces unnecessary strain. A system that is built around your needs will always feel faster than one built around assumptions. In the end, Linux desktops feel faster not because of magic, not because of marketing claims, and not because benchmarks always prove superiority. They feel faster because they are streamlined, modular, transparent, and efficient. They respect hardware, they respect user control, they avoid unnecessary overhead. On identical machines, that philosophy manifests as responsiveness. You move your mouse and the system listens. You open a program, and it appears. You work, and the computer fades into the background, exactly where it belongs.